Hello and welcome. We use numbers every single day, but have you ever just stopped and wondered how we built our entire number system? Well, that's what we're going to do. We're going to go on a step-by-step journey to see how each new type of number was invented to solve a problem the old ones just couldn't handle. Think about it, right? We all start by counting on our fingers, but that's just the very beginning. The number line is this continuous, infinitely dense thing, packed with all sorts of numbers. So how do we get from just simple counting to finding and naming every single point on that line? That is our mission today.
Okay, so let's dive right in. And you got to start at the beginning, right? With the most basic, the most intuitive numbers that humanity ever needed. And here they are, the natural numbers. The name is perfect, isn't it? Because they're just, natural. They came from the absolute basic need to answer the question, how many? How many animals are in the herd? How many days until it rains? It's the simplest question, and these are the simplest numbers. What's so fascinating is that the idea of 3 is universal, but the symbols we use to write it have been on a wild ride. We went from things like Egyptian hieroglyphs to Roman numerals, which, let's be honest, are a real pain to do math with, and finally landed on the super efficient Hindu-Arabic system we all use. And that wasn't just a style choice, it was a total game changer for calculations.
So we can count things. We're feeling pretty good about ourselves, but pretty quickly you run smack into a huge limitation.
Exactly. I mean, what if you have $5, but you owe someone 7? How do you write that down? Or how do you describe a temperature that's colder than nothing? The natural numbers just throw their hands up. They have no answer. They're a one-way street.
So the brilliant solution was to invent the integers. By creating negative numbers, the opposites, and giving a special place to 0, our system suddenly got this beautiful balance. For every positive 3, there was now a negative 3. And just look at what happened to our number line. It wasn't just a ray starting at 1 and going on forever. It exploded into a full line, stretching infinitely in both directions. And with that, we suddenly had the power to talk about debt, elevation below sea level, and so much more. Okay, so now we have this infinite line of whole numbers. But what about all that empty space between them? This brings us to our next big problem. Yeah, if you have 4 cookies to share among 5 friends, how much does each person get? The integers can't help you. 4 divided by 5, well, that's just not an integer. We needed a new way to talk about the pieces, the fractions of things. And that's when we get the rational numbers. The name kind of gives it away, right? It's all about ratios. Any number you can possibly write as a fraction is a rational number. And boom, with that one simple but incredibly powerful idea, we suddenly filled in countless points between our integers. Now, when you write these fractions as decimals, you find this really neat pattern. They always do one of 2 things. They either just stop, like 1/2 is 0.5, done. Or they go on forever in a repeating loop, like 1/3 is 0.333. That repeating pattern is like the secret signature of a rational number. It's how you can always spot one. Okay, so our number line is looking pretty jam-packed now. We've got integers, and we've filled the gaps with an infinite number of fractions. So we're done, right? Are we, or are there still some invisible, sneaky gaps we haven't found yet? To answer that, let's go back in time to ancient Greece and look at a simple geometry problem that totally freaked them out. Just picture a perfect square, with each side exactly 1 unit long. Now, if you calculate the length of that diagonal line that connects the opposite corners, you stumble upon a number that shook the very foundations of their mathematical world. What is that number? The answer is the square root of 2. And for the ancient Pythagoreans, who believed the whole universe was built on beautiful, simple whole numbers and their ratios, this was a monster. They tried so hard to write it as a fraction, but they couldn't, because it's impossible. It literally broke their worldview, and legend says they tried to swear the discovery to secrecy. And here's why it was so weird. When you look at its decimal form, it just goes on forever, but it never, ever repeats. There's no pattern, no cycle, it's totally chaotic. And that means it can't be a rational number. The famous number pi is another great example of this strange kind of number. So a whole new category had to be created. The irrational numbers. These are the numbers that fill in those final tiny gaps on the number line, the ones that all the fractions, no matter how many there were, could never touch. And with that last piece of the puzzle, we finally have everything we need. we can now assemble the complete, continuous number line.
So how do they all fit together? A great way to think about it is like those Russian nesting dolls. You've got the tiny natural numbers inside the bigger integers, and the integers are inside the even bigger rational numbers. The irrationals, they're like a whole other separate massive collection. But when you take all the rationals and all the irrationals and put them together, you get the grand total, the set of real numbers. This set is complete. There are no more gaps. Every single point on the number line finally has a name. Our journey is complete. And of course, this wasn't just some casual thing. It took the genius of some incredible mathematicians back in the 19th century, people like Cantor and Dedekind, to really nail everything down and formalize this beautiful, complete system we now call the real numbers. So this brings us to one last kind of mind-bending question. We've filled the entire line. It feels like there's no more room for anything new. But what if there are other kinds of numbers that don't even live on this line at all? What could possibly lie beyond?